Okay, so my starting slide for this evening is our current image of the year, a magnificent solar prominence imaged in hydrogen alpha by Rob Parsons. And I thought that was especially relevant given our main topic for this evening. So good evening, everyone, and a very warm welcome to the Astronomical Society of Edinburgh's online meeting for February. I'm Neil Martin, current president of the Society. And for those joining us on Zoom, please can you now ensure that your mic is muted? Thank you very much. So we have two items on our agenda this evening, as usual. In a moment, I'll formally introduce our guest speaker for this evening, Dr. Alexander MacKinnon. And following Dr. MacKinnon's presentation and the Q&A, so get those questions ready, I'll close the session with a look ahead to what we have coming up over the next few months. So let's begin. Dr. Alexander MacKinnon is currently an honorary research fellow in the School of Physics and Astronomy at the University of Glasgow. Now, between 1991 and 2020, he was a lecturer and then senior lecturer there. Now, Alec was also a research visitor at Goddard Space Flight Center in 1984. And for those of you who don't know, that's a major NASA space research lab located near Washington, D.C. And he was also at the Space Sciences Laboratory in 2007. And this is an organized research unit of the University of California, Berkeley. And finally, a visiting professor at the Mackenzie University, Sao Paulo in Brazil in 2013. In addition to his subject matter expertise, Alec has a long history in adult education, specifically providing academic oversight of the University of Glasgow's in-house mature student access course. And this supports mature students from a wide variety of backgrounds as they learn how to study and learn at university level. I'll just finish my intro by saying that I hope this evening turns out to be one of the nice things that Alec wanted to do in his retirement. So, ladies and gentlemen, please pop yourselves off mute for just a moment and let's give a warm welcome to Dr. Alexander MacKinnon. So I'll stop sharing now and hand over to you, Alec.
Thanks very much, Neil, for that introduction. And good evening to the Astronomical Society of Edinburgh. It's a pleasure to be talking to you again. Haven't been for a few years, but we have met before. Let me see now. I need to share my presentation, don't I? So, my topic this evening, the title I've chosen is Touching the Sun, which is a phrase that was coined for press release purposes, really, by the Parker Solar Probe people. We'll be looking at two particular space missions, the ESA-NASA Solar Orbiter mission and the NASA Parker Solar Probe mission, which are exploring the region of space that we would call the inner heliosphere, the region well inside the orbit of Mercury, getting quite close even to the sun's surface, and reaching a point that we can say in a well-defined way that I'll talk about later, that Parker Solar Probe at least has actually spent some time inside the sun's corona. So there we go. A few introductory words just. We live in the outer layers of a star. The solar wind flows away continuously from the sun. It's variable in its properties. Sometimes there are explosive dynamic phenomena that take place in it. It sculpts the magnetic fields, the magnetospheres, the magnetically dominated regions around those planets that have strong magnetic fields, including our own. And it's the driver for the variable phenomena of space weather that we find. That generally, that phrase describes the conditions of, temperature and density and familiar things, but also the properties of the magnetic field in the space around those planets. including our own. It's no wonder that we would want to send spacecraft closer to the sun in order to study the drivers of those phenomena in closer detail. So we'll take a look, first of all, a quick overview. I bet most of you know these things already, but a quick overview of solar magnetic activity. So here's a picture in normal visible light of the sun, the sort of image you could obtain perhaps with a good telescope and a white light filter. It's not from today. I had a wee look at the sun earlier on today, but it's not very spotty at the moment. So I've chosen a picture from last October when it was a little bit more interesting. The screen, we've got the wee size of the Earth dot at the top there, haven't we? So the radius of the sun is 700,000 kilometers, more or less. It's a huge body on terrestrial scale. We could fit 109 Earths across that disk there. It's a globe of gas, of course, hydrogen and helium and smaller quantities of everything else. As we look into that globe of gas, we reach a very well-defined layer where it becomes pretty much opaque and we don't see any deeper. We call that the photosphere, and the glow of the photosphere at a temperature of about 5,500 degrees centigrade is what you see in an image like this. You also see the first indications of the sun's magnetic activity in those black patches on the surface. Well, they look black in an image like this. The sunspots. You can tell that we're looking at quite large objects in some cases there, if you just recall the size of the Earth and the wee dot at the top there. Sunspots are a couple of thousand degrees cooler than the surface of the sun around them. So they're still hot if you were to touch one, but because they're so much cooler, they look dark by comparison. They are regions of strong magnetic field, and the presence of those strong magnetic fields inhibits the movement of the gas towards the surface that's carrying energy up, making the surface hot to glow. Famously, the number of spots on the sun goes up and down in a fairly well-defined cycle. The graph here shows what's called the sunspot number. So the sunspot number is not precisely the number of spots you would see if you looked at the sun, but it's an indication of how spotty the sun is. And along the bottom here, we have dates starting from 1700. So 1700, 1720, 1740, coming all the way up to the present day, to 2026. And you can see that there's a fairly well-defined cycle. The numbers of spots goes up, it rises from a minimum in a time of about 5 years, and it reaches a maximum, and then it starts to fall away again over the next 6 years to reach a very low level of spots again, and then start to pick up again over the next 5 years. And this has been repeating quite nicely, as you see, for more than 300 years now. There's some suggestion of other longer term cycles superimposed on that. There's a possible 80-year cycle that you can see in the peaks of each cycle getting higher and lower again. But that's a level of things we don't need to say too much about today, although it's very interesting. And you can see at the very bottom right of the graph here that we're just past the peak of the current cycle, and we're in the declining stage now. Here's a wee close-up of a sunspot. It's a movie, actually. It shows the sunspot, it shows the dark central part known as the umbra, and the lighter, less completely covered region around the outside called the penumbra. And you can also see in this beautiful movie from the Dutch Open Telescope, which was on Tenerife, what's called the solar granulation. So the outer third of the sun is in a state of convection. The gas is, if you like, bubbling. Hot gas rises up and cools to its surroundings and falls back down again. And we'll set it going again. It's so beautiful. We should. So each of these things, they're called granules in the center. The cooler gas is rising up, the hotter gas rather is rising up towards us, which is why it looks a little bit warmer. And then it falls down again at the sides. and you see the darker lanes in between these granules. A granule is 800 to 1500 kilometers, so about 10 of them roughly is something like Earth-sized. You can see the clock at the bottom, that's a couple of hours. The granules are really important for the presence of the strong magnetic field regions that we find in the sunspots. Magnetic field in a sunspot is maybe 1,000 times stronger than the field on average that we find in the surrounding regions. And this continual up and down motion of the gas has an important role to play in concentrating the magnetic field and being responsible for those things. The other famous sign of the sun's magnetic character is the corona. Its very tenuous, extended outer atmosphere, which we normally only get to glimpse at the time of a total eclipse. If we were all in the room together, I would say, who has seen a total eclipse? And folk could stick their hands up and we could share our eclipse stories from Turkey or Prague or Ulaanbaatar or wherever. But we're not all in the room together, so you'll just have to keep them to yourselves. The corona it shines by, it's actually the same light that comes normally from the surface of the sun, but it's very, very faint. It's about a millionth as bright as the bright disk of the sun. So we only normally get to see it when the sun's bright disk is hidden by the moon for a couple of minutes. This very beautiful image, which I think is from the 1991 eclipse, shows the sort of thing that catches your eye if you see it. It's not round like the disk of the sun underneath it. It has these streaks that extend out into interplanetary space known as streamers and rays and jets. And it's clearly got other things going on that determine its shape and its irregular character. And the key ingredient, again, is magnetic field. We get our best view of the outer layers of the sun by moving away from visible light, by making telescopes and cameras that are sensitive to ultraviolet light and X-rays. And those are devices that we have to place on spacecraft above the Earth's atmosphere because those things are absorbed in the atmosphere. So here are three images from the same date. It's actually the 11th of January 2023. Here's a visible light, white light image of the sun on the left here, and we're seeing the photosphere, what we would call the sun's surface. The next picture along it's the same date, same time, but it's in ultraviolet light, a very particular place in the spectrum, which has been chosen to pick out particularly gas of about 50,000 degrees. And then in the right-hand side here, we see another picture from the same time, showing material at the temperature of the corona at 1 to 2 million degrees. So we see that above the sunspots, above these strong magnetic field regions in the solar surface, we see most heating of the upper atmosphere of the sun, so that it glows brightly in ultraviolet light. And we also see, particularly in the corona, a little bit higher again, higher temperatures, we see that we see the presence of these loop structures. The solar prominence, like that beautiful image that we saw at the beginning, those things have been studied from the ground with hydrogen alpha filters for a long time, but we get our best view of those phenomena, those loop structures, when we look in the ultraviolet. Above the photosphere, there's a region of about 2,000 kilometers thickness. It's quite remarkable that it's such a thin layer on top of the 700,000 kilometer radius of the sun. And in that region, the temperature of the gas shoots up from the 5,500 degrees centigrade of the surface to 1 to 2 million. And that's the temperature that we find in the outermost atmosphere of the sun, the corona. So this very narrow region is called the chromosphere, and most of this glow is coming from that region, just a few 100,000 kilometers above the surface, and then a wee bit further out and more extended we're looking here at the corona. And the thing that really we see in a picture like this is how dominated it is by the magnetic field. Let's look at a nicer picture. This is actually a movie, but I'll set the movie going in a wee minute. At temperatures of tens of thousands, hundreds of thousands of degrees of Kelvin, um, collisions between atoms are violent enough that electrons get knocked out. This happens all the time. There are very few neutral atoms in the outer layers of the sun. It's almost entirely ionized. It's almost entirely made up of ions and electrons rather than neutral atoms. So the constituents of the gas carry electrical charge. They're sensitive to the presence of a magnetic field. If you think back to school and tracing out magnetic field lines with iron filings, those magnetic field lines that you picture in that way, they take on almost a structural character in the outer layers of the sun. The electrons and ions can travel easily along the magnetic field lines, but there's a force that stops, the magnetic force stops them from moving very far across the magnetic field. So the loops, this loop here, this beautiful loop here, for instance, would have magnetic north at one end and magnetic south at the other end. And those field lines, the field lines you trace out with iron filings, the field lines that Faraday and Maxwell conceived of in an abstract way to demonstrate how the magnetic field works, they're abstract mathematical things, but in the outer layers of the sun, in anywhere it's ionized actually, anywhere the gas is ionized, they take on the character of structures. But structures rooted in the dynamic gas underneath, the gas of the convection zone. So they're always moving around, they're always evolving. Let's set this movie going and watch. Oh, there's a solar flare, a sudden release of energy when the currents in the magnetic field they get dissipated very quickly. The shape of the magnetic field changes, and the energy that's released in that goes to heating the atmosphere and making the gas move. Will we watch that again? It's really nice. Bang. But the other thing, apart from the bang, you notice really is those magnetic structures retaining their integrity. In a plasma, plasma is a word for a gas where nearly everything's ionized. In a plasma, the magnetic field and the gas get tied together in a way that's quite unfamiliar to us. If I was to wave a horseshoe magnet around in the room here, nothing would happen. Well, I might pick up a paperclip or something, but it wouldn't make the air move with it. But if I was to wave my horseshoe magnet around in the corona, in the sun's outer layers, then the magnetic field would make the gas move. If there's an explosion somewhere and it makes the gas move, the gas will carry the magnetic field with it. The magnetic field in the gas, the phrase that's used is frozen in. The magnetic field gets frozen in. The gas and the magnetic field evolve together. So, a wee quick look at the magnetic field concentrations in the surface and the corona, the magnetically dominated corona. Another aspect of the sun's outer layers we refer to by the name solar wind. The first suggestion of the solar wind was made in 1947 by a German scientist, Ludwig Biermann. He looked at images of comets like this beautiful Hale-Bopp image here. And if you remember Hale-Bopp, if you've been looking at some of the nice comets that have been around in recent years, you'll have noticed that comets often have two visible tails, a sort of yellowy dust tail, dust particles that have been blown off the surface of the comet as it comes in close to the sun and warms up, and also a blue gas or ion tail. And the two tails point in different directions. The pressure of sunlight is what drags the dust tail out, and it always points away from the sun. But this tail is made of gas atoms that have escaped from the surface of the comet. They've been sublimated from the surface of the comet. They get ionized by ultraviolet light from the sun, so they become ions, and they're sensitive. They don't point in the same direction as the tail of the sun, which is just driven by sunlight. They're clearly reacting to some other agent that's passing by the comet, and the other agent is the magnetized solar wind. So the presence of the magnetic field in the solar wind means that the ion tail points in a different direction from the dust tail. And Biermann suggested that this was the way to understand two tails of comets in terms of a solar wind, a continual flow of gas away from the sun. In 1958, Eugene Parker, the man whose name is on the spacecraft, showed mathematically that gas has to flow continuously away from the sun, basically because the corona is hot, it's at a couple of million degrees, and the far edge of the universe is cool. There's a pressure imbalance. Solar wind has to flow away all the time. But the means, the precise means by which the solar wind gets driven, that was another question. Parker Solar Probe was launched. It had Parker's name on it. He was the first. He passed away a couple of years ago, but he was the first scientist to have a probe named after him in his own lifetime. So solar wind flows away continuously from the sun. It carries any magnetic field with it from the regions that it starts in. We find it in two versions. They're called fast and slow, and they mean exactly what we say. When we look at the corona in X-rays or ultraviolet light, we find these extended cool regions. It doesn't shine so brightly, which are called coronal holes. In the coronal holes, the magnetic field comes out from the surface, but it doesn't come back down. We don't get closed loop structures as we do over here. You can make out some of the little loops in that structure, and over here and all the way around here. The magnetic field just comes out and it heads off into interplanetary space. So the gas can flow away more freely in these. And if we pass through that structure is maintained all the way out into the solar system. When we're feeling the solar wind flow from a coronal hole, then it's at about 800 kilometers per second, and we call that fast solar wind. When it's from the closed field line regions, it's going slower. It's more like 300 to 400 kilometers per second, and we call it slow wind. And if we pass through the boundary between slow and fast wind, that's one of the circumstances that can trigger displays of the northern lights. In the 1990s, the Ulysses spacecraft travelled away out. It went out to the orbit of Jupiter, and it used Jupiter as something to burrow round and head up to high latitude, and it passed over the polar regions. So it gave us measurements of solar wind speed all the way up out of the ecliptic. So what's called the streamer belt refers to the region close to the ecliptic, close to the solar equator, where these streamers extend out into interplanetary space. And in this region, we would find the solar wind at 300 or 400 kilometers per second, except when it's flowing away from a coronal hole, and then it might be more like 800 kilometers per second. So the height out of these spikes is showing the sort of speeds that we find. But when we go up to high latitudes, there are great big polar holes in the coronal holes in the polar region. And when we go to high latitudes, we find fast wind all the time. I like to show this photograph because I took it in my own back garden. It was the 10th of August, 24. One of the three beautiful displays of aurora that we had that year. And as you can see, it made a reasonable picture, even living with. I live on the south side of Glasgow, so Glasgow's light pollution, but still managed to get something discernible in the image. So it's either fast, slow wind transition or some of the more explosive events that happen on the sun that drive eventually displays of the northern lights. Now we come to Parker Solar Probe and Solar Orbiter. So there are several questions. The core of the sun, of course, is at a temperature of about 15 million degrees. And as you come away from the core, where the nuclear reactions are happening to keep it hot in the core, uh, the temperature falls off gradually until you reach the surface, until you reach the photosphere, and then it's 5,800 kelvins. It gets cooler for 100 or a couple of hundred kilometers above that. And then, as we said, through the chromosphere and into the corona, it shoots up until it's a couple of million degrees. So why do we find this tenuous extended layer of gas sitting on top of the sun at a much higher temperature? Why does it get hot again? What heats the corona is a major question of solar astronomy, but because the sun is prototype for understanding all the other stars, it's a big question for understanding stars generally. We've known for decades that other stars have coronae as well, glowing X-rays. So we can imagine a couple of different ways we might heat the corona. They're in the convection zone, the gas is always moving around. It's bound to generate waves and disturbances that travel out. So perhaps those dissipate and lose their energy and heat the corona. Or there might be lots of tiny flares. So the UV movie I showed a minute ago had quite a big flare. It was an obvious event, explosive event. But in 1980, some of our colleagues in Berkeley, in the Space Sciences Lab, they flew a sensitive X-ray detector, and they discovered that there were smaller flares than anybody knew about happening roughly once every few minutes. Microflares, they called them. They were about a millionth the size of the biggest solar flares that had been observed. So if we imagine that there are not just microflares, but nanoflares and picoflares getting more and more numerous, more and more frequent as we go to smaller and smaller events, perhaps all of these tiny little explosive things happening all the time could account for the heating of the corona. And then another question. Parker showed that the solar wind has to exist, but there's a more detailed question of what is it that drives it? What releases the energy that's causing the solar wind to travel away from the sun all the time? And how does the slow wind get away at all? Given that it would, at first sight, at first appearances, it would have to make its way across the magnetic field of those closed magnetic field line regions. Where is the boundary between the corona and the solar wind? How do we draw that boundary? Where do we find it? So it was these major questions of solar astronomy that drove the development of Parker Solar Probe and Solar Orbiter mission. Although we should mention, there had been a mission before that. The Helios mission went, well, to less than a third our distance from the sun, 0.29 astronomical units. And it was operating out there from 1974 to 1982, and it made at least one discovery we'll come back to. But there's a lot more to be done in that realm of space. So, first of these missions was Solar Orbiter. Solar Orbiter was launched in 2020, February 2020. At its closest, it will be at 0.28 AU, inside the orbit of Mercury. That's 60 solar radii from the sun's surface, 42 million kilometers. It takes 168 days to orbit the sun once, and we've been in routine science operations mode since November 2021. Over time, it will make its way out of the plane of the ecliptic to an inclination of 33 degrees, and it'll get a view of the solar polar regions. It already has a view, actually. How do you get something close to the sun? You can't just launch it into space and let it fall towards the sun because it has the same orbit angular momentum as whatever it was launched from. So we have to lose angular momentum in order to get our spacecraft closer to the sun. And the way that you do that is by going to Venus, giving Venus a wee push. Venus doesn't feel any difference, but the spacecraft loses some of its orbital motion around the sun, and then its orbit is modified so as it can come in closer. So launch on 9th of February 2020, and then there were a couple of close encounters with Venus, which changed the shape of the orbit, allowed it to go closer to the sun in December 2020 and August 2021. A second encounter with the Earth in November 2021, and that put it into the operational mode. And then it's going to have several more encounters with Venus. It's had a couple already. It had one in February last year. There'll be another one in December this year. And the purpose of these later Venus encounters is to move the orbit more and more out of the ecliptic. So it's currently at an angle of 17 degrees to the ecliptic. And from January 2027, from about a year from now, it'll be making its way to 24 degrees. And eventually in 2028, it'll be up to 2029, it'll be up to 33. It has already had its first view of the sun's south pole. Here's a representation of the spacecraft. It's a third hour distance from the sun. The sun is 9 times brighter looking. It has 9 times as much radiation per square meter to deal with as something would in near-Earth orbit here. So it has a heat shield on the front. It has solar panels for power, as you'd expect. It's about 10 meters. Sorry, 3 meters. It's about 10 feet tall. The long axis there is about 10 feet. You can see in the movie, it's got a big heat shield on the front, and you see the wee windows opening as well, so as the imaging instruments can peer out through the heat shield. Here's the heat shield at the top of the image here. There's a layer of titanium on the outside, and there are gaps. So there's an inner layer of aluminium and another gap to the spacecraft, and the gaps between the layers are what allow most of the heat to be radiated away as infrared to space rather than heating the spacecraft. It's got several suites of instrument on it, and they're in 2 broad classes. One of them we describe as in situ. So these are for making measurements of the gas, the plasma, immediately where the spacecraft is in its immediate surroundings. So there's a detector for energetic particles. That's a major topic of solar physics, the presence of energetic particles in the heliosphere. At the sun, there's a device for measuring the magnetic field, a device for analyzing the chemical composition of the solar wind, and a device for monitoring the waves in the plasma. And there are several imaging instruments. There's a telescope for ultraviolet imaging. There's a coronagraph, which hides the bright disk and lets you study the corona. So you can see things happening in the corona, and then you can start to make measurements of the state of the gas when those disturbances come past and so on. There are a couple of other devices for imaging, for looking at disturbances traveling across the solar surface. And the one that's actually of most interest to my own interest in solar flares, there's an X-ray imager, an X-ray telescope as well. One of the most interesting discoveries, I would say, from Solar Orbiter has been, it's related to the issue that we mentioned a minute ago of nanoflares and picoflares, and it's the discovery of tiny little bright points. They called them campfires. I'm not quite sure where this name came from, but if you have ever travelled across the continental USA and made your way to California, and you go across the desert regions, Nevada or New Mexico or wherever, and you're looking down and there's somebody camping and they've lit a wee fire, there'd be a tiny, tiny little glow you would see from your plane at 30,000 feet. And I guess that's how they picture them. It's as though you're traveling above at some great height above a sort of dark desert region, but there are tiny, tiny little bright spots. So these tiny, tiny little bright spots are quite interesting. What's making them brighten up are these picoflares, tiny little energy release events. Those questions still have to be fully opened out, but they were a very interesting discovery. Here's another example of what you can do. Energetic particles arrive at Earth from the sun following solar flares, and they come in two versions. Uh, what's called a gradual energetic particle event. By energetic particles, I mean electrons and ions, and an impulsive event. And this doesn't really refer to the duration of the energetic particles as they arrive at the spacecraft, as they arrive at Earth. It actually refers to the phenomena at the sun that they're believed to be connected with. So the impulsive events are believed to come straight from solar flares. The gradual events are believed to be accelerated in the coronal mass ejection that travels away from the sun after a flare. So Orbiter was able, with its imaging instruments, to spot the occurrence of a flare or the ejection of a coronal mass ejection, and then to actually measure the energetic electrons and ions that arrive and determine definitely did the so-called impulsive events, which are rich in electrons, did they really come from a solar flare? Did the gradual events with a lot fewer electrons, many more ions, did they really come from a CME? And they were able, with in situ measurements for the first time, to confirm that picture. So that's a really interesting thing. We'll have more to say about Orbiter in a minute and other things that it has seen, but we'll turn now to the Parker Solar Probe. So Solar Probe is a mission to go very close to the sun. It'll go to 9 solar radii. It'll go to the upper edge of the region in which the solar wind is accelerated. And it also has had several Venus encounters with the aim of modifying its orbit until it can get that close to the sun. It's had lots of wonderful publicity, of course. It's doing an amazing thing. At perihelion, at the closest to the sun, it's traveling at 700,000 kilometers per hour. It's the fastest man-made object. It also carries a set of instruments, an instrument for measuring the magnetic field and the oscillations, the waves in the plasma locally, an instrument for looking at the corona, invisible light, again, to study the disturbances that you hope you're going to feel the consequences of, an instrument for detecting energetic particles, and another instrument for analyzing the composition of the solar wind and the lower energy particles. The energetic particles, I have to say, they sound a little bit esoteric. They are electrons and ions that are traveling much faster than you'd expect on the basis of the temperature of the corona and the solar wind. They're a thing that happens everywhere in astrophysics where there's plasma, probably. So what we learn from the sun gives us ground truth for understanding those phenomena in more remote locations, in hotter or cooler stars, even exotic places like white dwarf atmospheres, and in the vicinity of neutron stars. The means by which explosive events in a plasma gives those particles high energies it's a very scientifically interesting question. It's also got some technological implications because those particles can be disruptive to spacecraft operations. I don't look very often at the Daily Mail, but I was amused that it had a big article about Parker Solar Probe, which actually wasn't bad. It covered the science fairly nicely. The imperial units, temperatures in Fahrenheit and so on, really makes your hair stand on end. But apart from that, it wasn't a bad article. And they have this nice diagram here, which highlights some of the key features, like the thermal shield. It's going much closer to the sun again than solar orbiter. It's just different technology. It's a thick carbon composite, 4.5 inches thick, and it shields the spacecraft. Its solar panels retract when the solar probe PSP is getting very close to the sun. And in the diagram here, we've also got some words about the various other instruments that we mentioned already. Parker's solar probe has passed through the corona. What do we mean by that? How do we draw the boundary between the corona and the solar wind? The key idea there is actually the idea of an Alfvén wave. An Alfvén wave is a wave which can exist in a plasma. If you think of your magnetic field lines, if you think of those loops, you think of the magnetic field lines traveling straightforwardly from south to north. It's a wiggle in the magnetic field that travels along. In a plasma, the field lines, as we say, they get tied to the gas. They get tied to the plasma, and if you push it sideways a little bit, the field lines then have mass attached to them. They have a sort of tension. They're like a taut string, so you can drive a wiggle on it. It's called an Alfvén wave. Alfvén, the Swedish physicist, won the Nobel Prize in Physics in 1970 for his prediction of Alfvén waves. They're a fundamental thing in a plasma which has a magnetic field threading it. The stronger the magnetic field, the faster the Alfvén waves travel. The more tenuous the gas, the faster the Alfvén waves travel. But it's a fundamental speed in a plasma. Why is it important? Why am I introducing it here? Well, they're a fundamental property of a gas or a plasma. You give the gas a poke somehow, and waves are what will travel away from it. So they carry energy, they can deposit that energy somewhere else, they can make things happen somewhere else. They're the things that carry signals. So what happens if you drop a stone in the water? You make ripples in the water. You make water waves at the surface, and they travel away and they hit the edge of your pool or side of the harbour wall or whatever. The waves are the fundamental thing in the plasma, in the gas, that will carry information, carry signals. And in a plasma, in a magnetized plasma with a magnetic field, they do it at the Alfvén speed. So there's this region of a couple of solar radii where the solar wind picks up its speed. We can draw a circle around the sun. Near the sun, the solar wind is traveling slowly. It's traveling at less than the Alfvén speed. But we picture coming further and further from the sun, solar winds going faster and faster. Eventually, it's going to be traveling faster than the Alfvén speed. So what happens if something happens out here? Let's say Parker Solar Probe explodes and it drives waves. The explosion of the spacecraft drives waves. The waves are going slower than the solar wind. They're going to be carried away from the sun. No signal out here beyond this Alfvén surface, where the solar wind is traveling faster than the Alfvén speed. No signal can make its way back to the sun. If the same thing was to happen in here, inside the Alfvén surface, then the solar wind is moving outwards, but the Alfvén waves are going faster than the solar wind. They can make their way back to the sun. They can impact the solar surface. They can affect things behind them. Out here, you're divorced from the solar surface. I mean, light, of course, can still reach the solar surface from out here, but mechanical things can't in the plasma. So we call this the Alfvén surface. Inside the Alfvén surface, we're in touch with the solar surface. We're touching the sun. Outside, we think of it as solar wind rather than corona. In 2021, there was a 5-hour period. The path of the spacecraft is represented by this red line here, where it was between 19 and 18 solar radii above the surface, and it passed through a region where the solar wind speed was less than the local Alfvén speed. So, in this mechanical sense of waves travelling through this period here, it's a sort of a 5-hour period altogether, the spacecraft was in the corona. So this justified a press release, and the phrase that was used was Parker Solar Probe touches the sun. It was really in contact with the sun at that point. The details of the magnetic field lines are represented in this picture over here, and this is latitude and longitude in the sun. Where the field lines go purple in colour, that's where the spacecraft up here is actually inside the Alfvén surface. Now, the sun on Earth, the strong magnetic fields are at the poles. On the sun, that's not the case. The strongest magnetic fields are in the sunspots or the magnetic active regions, even if they don't develop dark sunspots. So we expect this Alfvén surface to be complex and irregular, and that's exactly what was found. The most important thing that Solar Probe has been involved in is shedding some light on how the solar wind is driven. And the starting point for this discussion is the idea of a magnetic switchback. This is a thing that was discovered by Ulysses in the 1990s and even by Helios before that. But Parker Solar Probe saw many, many more of them, and Solar Orbiter has observed possibly the events that generate them. So the magnetic switchback is, you suppose you're traveling towards the sun and the magnetic field is coming away from the sun. It's pointing out from the sun. The field lines are pointing out from the sun. But you pass through a region where the magnetic field seems to turn round, and it points back towards the sun briefly, and then you keep going and it turns round again. So if you were to draw if you were to draw the field lines, they would have an S shape. They would be traveling out towards the outer solar system, and then they would turn around and they would go in the opposite direction for a little bit, and then they resume going out again. And these magnetic phenomena, which spacecraft encountered and measured, because they've got instruments that measure the magnetic field, we were called switchbacks. Parker Solar Probe discovered lots and lots and lots of them as it got nearer to the sun, many, many more than were expected. So ubiquitous that you begin to think there's something basic to the existence of the solar wind. What could they be? Well, that's hinted at in this movie here, which is in ultraviolet light, and it's from Solar Orbiter. And see the field lines that form, they have that sort of S shape. But this is some sort of explosive event. This is a release of energy in the plasma, and the release of energy has happened in a way which has generated this S-shaped structure here. Let's just watch that again. So what people think is happening is here's a bit of a coronal hole, possibly, magnetic field lines traveling freely out into interplanetary space. Here's an active region with the closed magnetic field lines coming out the surface here, back into the surface here. But as the gas moves the magnetic field around, these things can come together. And a region can form where the magnetic fields are going in opposite directions and they meet up. Then there's a region where the magnetic field gets really weak. And in those regions, the field and the gas are not so strongly coupled anymore. And in those regions, you can get explosive energy release. You can get currents formed. And afterwards, the magnetic field has a different shape. So some of these field lines that were closed field lines here have become detached, but with this S shape, which reflects how they came into being in the first place. And then this thing here will travel away from the sun with the switchback shape. And you believe that's what's been seen in the previous movie. Parker Solar Probe, close to the sun, discovered lots and lots of places where the gas was flowing away in narrow, well-defined regions, even down to the 100-kilometre scale. Tiny, 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 lots and lots and lots of them. Further out, they're accompanied by magnetic switchbacks. So you think perhaps the formation of the switchback, this energy release from the magnetic field thing that lets it travel away from the sun, is also connected to the generation of these flows. And they're also accompanied by energetic ions, which you expect from those regions where reconnection takes place. That's this business where the magnetic field lines can change shape and energy gets released from the event. So you think what is happening is that at the boundary of the coronal hole, um, closed magnetic field lines and open magnetic field lines are meeting all the time. And these tiny little energy release events are taking place all the time. They're generating these magnetic switchbacks that travel away from the sun. Because they involve electric fields, they produce energetic ions and they generate a flow. These things are numerous enough and they include enough energy that they can drive the solar wind. So it's a 70-year-old question in solar physics. The idea of interchange reconnection, I should have put that in bold or red or something, happening where the open and the closed field lines meet. It's not a new idea, but these are actual measurements in the solar wind which seem to be showing that's what's happening. And here's an amazing movie of lots and lots of these little jets getting driven. Basis of the fast wind in a coronal hole. Lastly, one of the other lovely things you can do, this is a horrible messy slide, I'm not going to say very much about it, but Parker Solar Probe is close to the sun. There are other spacecraft, there's Solar Orbiter, a bit further out. There's the stereo spacecraft, they run ahead and behind of Earth. They give you a multi-directional view of the sun. So by combining measurements from these various spacecraft, you can watch the development of coronal mass ejections and then you can monitor the actual conditions as they pass one of the other spacecraft and so on. And that's giving us new insights into how those things develop in space before they arrive at Earth, if they do, and generate displays of the northern lights. So, an almost unexplored domain of space, the proximity of the sun, the inner heliosphere, it's giving us very great, exciting new insights. The discovery of the campfires might have something to say about heating the corona. The switchbacks and their origins. What happens at the boundaries of the coronal holes, they may well be key to driving the solar wind. Three-dimensional studies of coronal mass ejections, flares, energetic particles, involving several spacecraft in either at least widely separated, some of them in the inner heliosphere, are yielding all sorts of new insights. And as well as that, Parker Solar Probe has for the first time actually passed through the corona. It has touched the sun. It's quite a technical subject. I hope I've managed to make some bits of it accessible. Thanks for listening.
Well, Alec, I can safely say that you've absolutely made that accessible. Um, I can't believe how much science is packed into these amazing instruments and that they can operate in these amazing conditions. So everyone, if we can come off mute and thank Alec before we head to the questions. So Peter, I think you're monitoring the chat for us. Do you want to pick up on the questions?
Yeah, I think Nigel had a question. And then Nigel, do you want to unmute and ask your question?
Yes, thank you. Superb talk, Alec. Thank you very, very much. I just wondered the corona. We're saying between 1 and 2 million degrees centigrade. Obviously, much hotter than the actual photosphere. Is it that temperature? It's quite a wide area. The corona. Is it that temperature evenly across its width, or does it cool off very fast towards the outer edge of the corona?
It doesn't cool quickly at all. I think conduction is quite effective actually. Even out at Earth here, the temperature of the solar wind is hundreds of thousands of degrees.
All right, okay, and that's a mystery still as to why that should be as hot as that.
Yeah. I remember discussing this at the very first first big conference I went to. I was speaking to a Dutch guy who was working on coronal heating, and his comment was, "Well, we can think of 2 or 3 ways of doing it, but the problem is deciding which of them is actually the one that's operating." Many people like the idea of nanoflares and picoflares, but depending on how you look for them, depending on precisely on how you look at them, so using penetrating X-rays or less energetic X-rays or ultraviolet or visible, it doesn't look like there's enough of them actually, these tiny wee flares to do the heating of the corona. So that brings you back to, well, maybe some years ago, people used to talk about currents. There are certainly currents that flow, certainly in the closed field line regions. And of course, current flows in a wire. There's some resistivity in the wire that makes the wire heat. Currents flowing through the plasma in the corona may be heating it. I've not heard anybody talk about currents for a long time. So probably the best candidate is waves. As we saw in the lovely Sunspot movie, the outer layers of the sun are continually in motion. They will drive Alfvén waves and Alfvén type waves, which will travel out into the corona. So if those waves find themselves in a region where they're losing energy more rapidly, they're probably what heats the corona actually.
Okay. Thank you very much.
Yeah.
Alec, I had a question. I presume with the Parker Solar Probe flying so close to the sun, it must deteriorate in some way. I was just wondering if there's key science it has to complete before it eventually deteriorates to non-working.
That's a good question. As you would, a space mission, when it's scoped out initially, there are scientific aims, there are sorts of measurements that they would like to achieve. My guess would be that Solar Probe has already achieved many of those. I think the biggest the biggest aim for it was understanding the origin of the solar wind. And, when it was originally conceived, it wasn't going to be in orbit around the sun as has developed. It was going to go very close to the sun. It was going to go to within 1 or 2 solar radii above the surface and do an incredible fast slingshot, sample those regions, and then go shooting off away into the outer solar system. And some of the solar wind scientists were annoyed that Solar Probe, as it developed, felt like a compromise. It felt it wasn't going to go close enough to the sun. I think it's been fortuitous that the jets, the picojets as they call them, the magnetic switchbacks, those things retain their identities even out to the regions that Parker Solar Probe is sampling. I think maybe it has if it was to stop tomorrow, the flood of papers would not cease. There's lots and lots of publications on all aspects of the solar atmosphere, the solar wind, a subject that's even more esoteric than the things I've spoken about, which would be the state of turbulence in the plasma. It's a naughty topic to talk about, but it's also one that's very important for understanding things that plasmas do. I have to confess, I have forgotten the initial period of the mission. I suspect some of its science aims have been achieved, but there are still useful things that you can do with a mission like that as long as it keeps operating in terms of space weather monitoring. So CMEs, conditions within the CMEs, their likely impact on Earth if they come in our direction and so on. That doesn't quite answer your question, but I hope it goes some way towards it.
It does, thank you. That's there's no more questions on Zoom unless somebody wants to pipe up now.
I have one of that, please. I think when they started looking at the results from the Parker Solar Probe, there's some evidence that there's absence of dust around the sun. I think it was a theory beforehand that there'd be this sort of dust-free area around the sun. And I think some of the initial results were that saying that was the case. Do you know if that was concluded that there's this dust-free area around the sun?
I'm sorry, I've paid no attention to dust. I plead total ignorance on that question.
Well, yeah,
Sorry.
you're not like in our household then. Thanks.
Okay, shall we pass over to Will? Will, do we have any questions from our YouTube audience?
No, we don't have any, but after that fantastic talk, I've got a question, if that's okay. Absolutely terrific talk. I just sort of wondered if, presumably, there must be data coming back with the temperature that the Parker Solar Probe is experiencing. And it must be pretty severe, especially if it sort of touched the sun, as you say, just managed to get in there a little bit in there, nipping into the chromosphere, a fraction of it. Simply because burning up of material, space debris coming through our atmosphere sort of burns up at a few thousand degrees. So I just wondered if there'd been any sort of hint of a maximum temperature that the Parker Solar Probe had successfully saved itself from, if you see what I mean.
Well, there's two aspects to that. One of them is the temperature that the spacecraft attains because it's being blasted by sunlight at a much greater distance than our own. And the carbon composite shield on the front is designed to save it from that. I think it will not get more than 380 centigrade. So quite a high temperature, but much less than the conditions in the gas surrounding it. The corona around it is at a temperature of 1 to 2 million degrees, but the corona is extremely tenuous. The pressure there is it's a millionth of what you'd experience. It's a little more than a millionth. Actually, it's 10 to the minus 12 of the gas pressure you would experience standing in the room here. So although the temperature is high, in terms of your massive spacecraft, there's nothing there. That's less of a hazard than the heat than the heating of the spacecraft by sunlight.
Fantastic. No, it's I must admit it sounds quite an achievement to have achieved that, and especially with the heat shielding and stuff. But yep, I think everybody's enjoyed your talk on YouTube. Marvelous. Thank you.
Thank you. But both Solar Probe especially is fantastic engineering achievement. Absolutely. I'm a solar physicist. I'm interested in solar flares. I am not a spacecraft engineer, but I've got enormous admiration for those people, what they've achieved.
Excellent. Thank you.
Wonderful. Thanks, Will. Okay, let's thank Alec again for his wonderful talk and for answering our questions this evening. Alec, thank you so much. And as I said, you're welcome to hang around and hear what we've got coming up in the next few months as I bring the evening to a close. So let me just share my screen again.
To listen to all that.
Okay, coming soon then I'll close out the evening and cover what we've got coming up for the next few months. So just the one event remaining in February, if I can do my bit and sort the weather out. Starting from this Saturday, the window is open for the rescheduled, previously weather-affected Cosmic Explorer event with Midlothian Library Services, which Andrew Farrow is coordinating, and we'll confirm a specific date as the weather relents, and that might lead to a kind of short notice scenario. So keep an eye and ear open for that event if you're helping out. Moving into March, on Friday the 6th, our main AUC meeting. Our guest speaker will be Bill Barton, who is the Deputy Director of the History Section of the British Astronomical Association. And in his presentation, Bill will outline the history and discoveries made using the biggest telescope in the world that existed from the 1840s until just before World War I. And surprisingly, this instrument wasn't at a national or university observatory, but at a nobleman's country estate in rural central Ireland. So that promises to be a fascinating talk. Our mid-month online meeting on Friday the 20th, our guest speaker will be Dr. Noel Castro-Segura. We're still staying with a stellar topic, but this time it will be the subject of binary stars and stellar cannibalism. So a different look at stellar activity. And more details will be published shortly about that talk. Moving to our members and other events section, our standard online imaging and observing group session for members only is on Wednesday, the 11th of March. And then we have a few other activities going on. Monday the 23rd, myself and Nigel are travelling down to Peebles to present talks to Tweeddale Astro Society. On Friday the 27th, so later that week, we are doing an outreach event at the House of Bins in West Lothian, another public stargazing event. And on Saturday the 28th, one of our members, Brian Lawrence, another connection with the BAA, Brian is presenting his talk, Adventures in Auriga, at the Deep Sky Section annual meeting in Cheltenham. So you'll see a lot more of Brian's images in that session. So action-packed March. And then finally in April, our main AUC meeting, we don't have a guest speaker that night. Instead, it's members night. So the stage is all yours. And hopefully you will have seen the items in the newsletters and you know to contact Nigel Goodman if you have something you'd like to talk about. So a collection of small talks for members to share info. And Friday the 17th, our mid-month online meeting. Again, we're sticking with a stellar topic. Our guest speaker is Anwesha Sahu, who is a PhD researcher at the University of Warwick. And the working title of her talk is White Dwarf Pulsars. So again, we'll publish more details of that shortly. And in the members and other events section, our imaging and observing group session is on Wednesday the 15th. Check I've got that date right. Yeah, Wednesday the 15th. And on Friday the 17th during the day, that's going to be a busy day. We'll be back in East Lothian at Archerfield. We are attending the Wonders of Space event, which is part of the wider science festival. And we'll be doing some solar observing. So again, a close connection to our nearest star. And also at that event, the imaging and observing group photo display will be up for public viewing. And note that all of this information will be available on the events calendar page of our website as it becomes available. So we've got a good couple of months coming up while it's still dark, and we've got some solar observing thrown in to boot. So that brings us to the end of this evening's agenda. Thank you for joining us on Zoom and on YouTube. I hope you enjoyed the evening. I certainly learned a lot about the Parker Solar Probe and the Solar Orbiter from Alex's fascinating talk. So I hope you enjoyed it as much as I did. And I look forward to seeing you at future events. So for now, I wish you all good night. And of course, fingers crossed for those clear skies. Thank you very much.
Good night.